Okay. This talk is about an attempt to formalize GDTs as they are implemented in OCaml. And I will try to give you a bit of context. Well, GDTs in the programming language of OCaml, a major problem is principality of inference, which is known to be difficult. In many cases, actually, language decide just not to do anything about it. Well, require to give full types for GDTs. But in OCaml, we could prove that we could do inference and still be principal by using a concept of ambivalent types, which allow to detect ambiguity escaping from a branch in pattern matching. Here, I'm giving you an example. So we can define equality as we will define it at Coq. And now, suppose that I have a function that receives a witness. So in order to be able to receive an equality witness between A and int, we must first introduce A as a rigid type variable. Now I have an inequality witness. I receive also X of type A, and I'm opening the witness by pattern matching on it. This allows me to compare X with 0. And here I'm inferring actually the return type. I have not given explicitly a return type, and I'm allowed to infer it because both branches are X, both branches have type A, and I can return a function that returns something of type A. Of course, we must be careful about principality. So in the next case, function g, I return either X or 0. Locally, it's okay because A and int are equal. But if you think from outside of the function, we must decide whether we should be returning A or int. Since we have no good criterion to decide it, we have a principality problem. And in OCaml, this leads to an error. This has to be an error. So how does this work technically? The idea is that types that rely on GDT equations are represented as ambivalent types, which are a form of intersection types. But the point is that ambivalent types are only valid when equations are available. The relations on the equation is only implicit. But this means that in particular, you cannot have ambivalent types at top level. They would automatically become ambiguous and turned into errors. So for the first example, why does it work? Well, first we pattern match. So we have the equation A equal in, then we compare X to 0. Here X ends up being given the ambivalent types A and int because we want it to be able to use it as an int too. But this is a local use, so no problem. And then we return X, but these two X's in both branch are actually instances of A. So they can be given just the type A, and we can return A, just a function that returns A. In the next example, we have one branch that must have at least type A, since it's X. The other one is 0, it must have type int. So as a result, we will end up having a return type being A and int, which is okay locally, but becomes ambiguous when we leave the scope of the equation. So this results in this error. Of course, the user can solve these ambiguities by adding type annotations, which work in this context by separating inner and outer types, and in this way, hiding the internal ambivalent type. So here, for instance, I can write the annotation on the if then else construct, either return A or int, and this works in both cases. Of course, for cleaner programming, OCaml lets you write the annotation outside, but this is another story. So all this is very nice, and we thought we had a proof and everything was principal. But when looking for reduction rules, validating subject reduction, we came up with the following example. Here, I'm using two witnesses. One that says that A is equal to B, and the other saying that A is equal to int arrow int. And I'm receiving a function G of type A, opening the two witnesses and applying G to 3. Well, since A is supposed to be equal to int arrow int, this application is correct. And what happens is actually OCaml will infer this type. And if we open in this order, it will infer that the result type is B. But if we open the equations in the opposite order, it will infer that the result type is int. So this is strange. And clearly, this is not principal. And actually, it turns out to be a bug in theory that the ambivalence of G is not propagated to the result of the application G3. So we are, as a result, we're not able to detect the ambiguity. So of course, we want to fix that. But when we fix such a bug, clearly this denoted that there was something wrong in the reasoning, and we want to be sure that we don't have another bug left. So it would be nicer to be able to prove that in Coq. And fortunately, we already proved soundness and principality for another fragment of OCaml, and using a graph representation of types. What this is mean that we're using a graph representation of types is that we have judgments where the type is just a type variable, and the concrete structure of the type is this kinding environment with a mapping from type variables to kinds, and the kinds describe nodes in the types, if you will. And it appears that by just enriching the information in kinds with a concept of rigid variable passes, which I will explain in the next slide, we can represent correctly ambivalence and fix the problem in the previous slide. So principality is going to be hard to prove, but as a first step, subject reduction is already a good benchmark for well-behaved systems. So this is the first part we are trying to prove. More details about the type system. I'm not going to give you many details, but just show you how we can encode the following types. So the node alpha, which corresponds to the structure ambivalent types beta, arrow gamma, and rigid type variable A. So we're encoding it as the alpha in the context of this kinding environment, where alpha is associated with the kind, with represent an arrow type, with domain beta, codomain gamma, and annotated with the rigid variable A to denote the ambivalence. And the way we denote the propagation is that we require also that beta be just a type variable, so bullet kind, but annotated with a.dom, and gamma is also a type variable, but annotated with a.cod. So the language itself is going to be ML extended with type annotation, equation introduction, rigid variable introduction, and equation elimination. Our typing judgments are M as type alpha under equation environment Q, kinding environment K, and typing environment gamma. And for this typing judgment is going to imply that K is well formed under Q and gamma is well formed when formed under Q and K. I'm not going to explain all the typing rules, but very shortly, I just explain the use rule. So how am I going to type the use of witness M1 in the typing of M2? The idea is that we want M1 to be a witness of the equation T1 equal to 2. For this, well, we translate first this type into a graph type. And we require that there is a substitution mapping from this graph type to the graph we are using in the derivation here. And that M1 in this graph has type theta of alpha 0. If this is true, then we can use the equation in the typing of M2. How are we answering that the ambivalence is not going to leak? Is actually here we see that K has to be valid under Q alone. So it cannot let leak any ambivalence. If you want actually in the derivation of M2 to use the equation, we should extend the Garrigue environment by using this kind GC rule. So this rule already ensures that ambivalence is not leaking. Then about our Coq development. So it was based, as I said, on previous work, a certified implementation of ML with structural polymorphism and recursive types. Itself, it was based on Arthur Chargaro's development using locally nameless combined quantification. So in our development, we have avoided algorithmic unification in the type system by interpreting Q as the set of its rigid unifiers. And we already finished the proof of the substitution lemmas, but it remains a number of interesting cases in subject reduction, particularly how to propagate type annotations in type applications. The interesting case, of course, if you are annotated with a rigid type variable, you want to distribute it by using the codomain and codomain. And also about observations about what we've been doing so far is about the challenges and benefits of starting from a legacy code base. So in many cases, when you have such a code base, you will discard it and start anew. But our experience is the code base is old, but updating was not that difficult. So for instance, freshness of variables relies on automation, and this is easily broken, but we could fix it. Many interactions mean many new lemmas, of course, and longer proofs. This you cannot avoid. But there was no need to revise the overall structure of proof, and we experienced no major technical stumbling blocks. So it looks like this was a great boon to start from existing development. And we can say that local nameless quantification still seems a very good fit for graph types. There are practical questions such as would it be better to switch to a standard decision procedure for set disjointness rather than using ad hoc LTAC tactics? But we will decide it later. That's the end of my talk.
Right. Thanks, Jacques. Maybe we can have time for one quick question.
I have a question.
Go on, Francois.
Thank you. Hi, Jacques. I have a question about the first example on slide 2, I think, which is accepted.
Yes.
I'm curious about what happens if I, about the first example, yeah. What happens if I annotate and declare the return type to be int? Is it accepted?
Oh, this is fine. You can force it to be int. This means that internally you have an ambivalent type, but you will have resolved it like you would have resolved it here.
Okay, but then this means the system doesn't really have principal types, because I can manually annotate with a type which is not an instance of the inferred type.
No, it does not have the principal type of the naive type system, but it has principal types in the ambivalent type system.
Okay, thank you.
All right. Thanks again, Jacques. Maybe if you could please stop recording.
Yes.
And
oops.